Hello, algebra students. Welcome to Statistics and the Normal Distribution. So we don't really understand what a normal distribution is yet because we haven't actually talked about it yet, but go ahead and watch the video and then you can come back and look at this adorable joke and you'll understand it a little better. But this cute little rhyme should help review a little bit for you what we're talking about with statistics, the basics of statistics. Hey diddle diddle, the median is the middle. You add and divide for the mean. The mode is the one that repeats the most, and the range is the difference between. That's super cute. I like poems. Poems are fun. But gives you a little bit of review of the stuff you already knew. Let's jump in and talk definitions first. Measures of central tendency. A measure of central tendency indicates the, quote, middle, unquote, of a data set. That can include the measures of mean, median, and mode. So really, when we say middle or average, we don't have to be talking about the arithmetic average or the mean. When we're saying average, we're talking about the number that best describes the data. So that average may not always be the arithmetic average, the mean. Sometimes it'll be something different. The measure of central tendency used to describe a data depends on the data set. If the most common value describes the data, you use the mode. If I did a survey of all of the 7th grade or all of the 8th grade and said, what's your favorite flavor of ice cream? That's the mode would be the answer that would give us the most favored flavor. If a set includes outliers, so if you have a set of data and it's salaries of Americans who, or individual people who live in Hampton, well, if you count everybody and then you include someone who happens to be like a movie star who happens to live in Hampton, then that's an outlier. The median is a better measure because outliers affect the mean. If a set includes no outliers, you would use the mean. Now, I'm not going to ask you right now to come up with which one to use, but I do think it's important that you know this, so please make sure you copy down the information on this slide. Feel free to pause it and then continue, if necessary. But let's go on to looking at how we find each of these. So pause your video. Go ahead and copy it, including the examples, so you have that information, and I'm going to go ahead and walk you through it once you've copied it. So pause it and copy. But I'll go ahead and talk about it now on record here. The mean, sum up the data values, divide by how many you have. Of course, we know that one. It's mean to make me, or to have me make you find the mean of a set of data because, adding all those numbers is such a chore. Well, you have two benefits now. You have the TI-84 Plus, which means you can see the math on the calculator screen, and you also have the benefit of the stat key. So we want to remember that when we're using the calculator, that calculator can really help alleviate some of the difficulties we have in finding mean and median and so on. Mode it will never be able to find for you, but we'll get there in a minute. The median for a data set listed in order, it's the middle value of an odd number of data values, or it's the mean of the two middle values if you have an even number of data values. They happen to give us a set here that has an even number of data values, so you average the 3 and the 4 together and get 3.5. And 3.5 is halfway in between 3 and 4 as well, if you think about it. Mode you have to do with your eyes and your brain. Got to find the one that occurs the most. Excuse me, sleepy. You can have more than one mode. In this case, 3 and 5 are both the modes. You can have no mode at all. Depends on the data set you are given. A measure of variation is different from a measure of central tendency. A measure of variation describes how the data in a set are spread out. How they're spread out. And that's what we're going to devote the rest of this video to. We'll go back and we'll review practicing with mean, median, and mode. But right now, we're going to focus, for the rest of the video, we're going to focus on measures of variation. So this should actually say variance. Let's fix that real quick. Make sure you fix it in your notes, please. Variance and standard deviation are measures that show how much data values deviate from the mean, how far they all are from the average. So these two measures, variance and standard deviation, they tell you about how data values are different from the average, how far they are from that average. Okay, so variance and standard deviation. So as we said, these are measures of how spread out a data set happens to be. You have two formulas. You have the formula for variance, which you see right here. I'm going to outline it in green. And you have this formula for standard deviation, which is super similar except that instead of sigma, it's the square root of that, sigma squared for variance, it's just sigma. So they are very closely related. And it's a question of following the steps of actually finding the standard deviation or the variance. And you're going to do that with a couple of steps. You're going to start by finding the mean. Okay, now the mean is not just represented with the word mean, it's also x with a bar over top, and this Greek letter mu, which is like, you sound like a kitty. Mu is the symbol for the mean. You find the difference between each of the values in the data set and the mean. So you're finding the variance, the deviations, the differences between them, the deviations, differences. You take each of those differences and you square them. Then you take each of those differences and find the mean of that set. So take all of those squares and you find their average. And that's what this formula is actually asking you to do. Sigma is a Greek letter that represents sum of. Sum of what? Well, whatever comes after it. So this is sum up all those squared deviations, divide by how many you have. If you were looking for the variance, you'd be done. If you wanted to find the standard deviation, you would take the square root of the variance. All right, so here we have a set of data. We have 6 values, 52, 63, 65, 77, 80, and 82. Start by finding the mean. So remember that the mean can be represented with two different symbols. You're going to add them all up and divide by how many you have. It's perfectly acceptable to use a calculator here. I will be showing you the statistics shortcuts for this on your graphing calculator. If you recall, we used the lists for regression. You're going to use those lists and you'll actually be able to find the mean from the list. All right, so there we have the sum of all those values. I'm going to double check that I have the values put in my calculator correctly to make sure I'm not making a mistake. And I'm going to go ahead and find the mean. And I got 69.83 repeating. All right, and we are going to use exactly that value. That's 69 5/6. And I'm going to actually show you how you can store that information into your calculator and be able to use that information anytime you want on your calculator. But anyway, let's go on to variance. So what I'm going to do is I'm going to make a little table. The x value, so 52, 63, 65, 77, 80, and 82. Then I need the difference between those values and the mean. And then I'm going to square that difference. And then I'm going to add those all up. Find their average. And that's going to be my variance. So let's do that. Okay, so I'm subtracting every one of these with the mean. So you should do this. You can use your iPad calculator. Take a few minutes to fill in the table. I'm going to pause mine and fill it in so that we're not making our video way too long. Here they come. And there are differences. Now I know that these are all repeating decimals, and I'm going ahead and writing those down as repeating decimals on my paper. Now I need to go through and square them all. Now the reason I'm keeping the repeating decimals is that if I keep that, I'm going to be more exact. It's the same thing as if I was keeping them with fractions or mixed numbers. This would be 10 and 1/6. This is -5 and 5/6. So the benefit of the graphing calculator is I'll be able to show you how you can keep all that whole value without rounding it off, and then you'll be able to have more exact answers when it comes out here to the end. So the next thing I have to do is square every one of those. So let me go ahead and do that. Here they come. And there you go. So now I've taken all my values in the data set. I found the difference between each one in the mean, and I've squared it. Now I have to take that and find the average of that list. So I'm going to add all of those together and divide by 6. We'll go back through and look at this this set of directions in the formula in just a minute, okay? Let me go ahead and do that. Hold on. Here it comes. And for the variance, I got 115.1, and I'm saying approximately because I did round it off here at the end. Best bet here is to round off at the very end, and that's the variance. It's really, really hard for me to tell you what the heck does that mean. So what does that mean? Well, it's not really so much what does that actually mean by itself. It's what does it mean in comparison to other data sets. So we have to compare to another data set in order to figure out the significance to that of that particular number right there. Now, that's variance, okay? We found mean already. That was right here. Okay, there was the mean. There was the variance. Now, the standard deviation is we take the variance, which we have 115.1, and we square root that, and that gives me the standard deviation. And in this case, our standard deviation ends up being 10.7. And again, squiggly equal sign, because it is approximate. Again, what does that mean? We can't really say. We'd have to compare two data sets to be able to tell what that means. All right, so now that we've talked about standard deviation, we can talk about the normal distribution. It's a symmetrical bell-shaped curve, and it's defined by the mean and the standard deviation of a data set. The mean is located at the line of symmetry in the center. A location under the curve represents the likelihood of a data value occurring in real life. And the normal distribution is something we use in the real world quite a bit. Here's the basic normal distribution. In a normally distributed set of data with the mean in the center, 68% of the data fall within one standard deviation. So that means if our mean was 8, so say that our mean was 8, and our standard deviation was 2, then in this particular circumstance, 68% of the numbers would be between 6 and 10, somewhere between 6 and 10, and that's 68%. Now, this is true of all normal distributions. This is something that's really cool. I can show you lots of really cool examples in class. Remind me specifically of the quincunx. Quincunx. You'll like that one. That one's a really cool online one that you can view. Probably not on an iPad. We'll have to do it on the Promethean board. Now, if you go out further than that, 95% of the data fall within 2 standard deviations of the mean. And then finally, 99.7% fall within 3 standard deviations of the mean. So you can use these values to predict where a particular person might fall if you're talking about something that's normally distributed and so on. So we're not going to do problems like this too much in class, but I wanted you to see the significance of the normal distribution. The heights of American males are approximately normally distributed, approximately, because nothing is absolutely perfect, with a mean of 69.5 and a standard deviation of 2.5. Now, before I actually do this problem, let's actually sketch out what that means real quick. If this is 69.5, then one standard deviation below that would be 67. One standard deviation above that would be 72. One standard deviation above that would be 74.5. If I wanted to go the other direction, one standard deviation below that would be 64.5. Okay? What percent of adult American males are between 67 and 74.5 inches tall? Well, we can show that. We can see that. Look right here. Here's the 67. There's the 74.5. Now, if you go back and you look at the percentages you should have copied down a couple of slides ago, you actually should know what they are. Well, in this first section, this section right here, we already said that that's 68% of the values. Plus, this section right here, that's 13.5. So what percent of American adults are between those two heights? Well, it's whatever 68 and 13.5 are, so it's 81.5%. Now, that might be useful information to know if you're designing a car and you need to figure out how high to make the roof for people to sit in there. You want the vast majority of Americans to be able to sit in the driver's seat without hitting their head on the ceiling. Okay, if you're trying to develop a one-size-fits-all for something that the height would matter, the vast majority of people are in that range. And this is why the normal distribution is why not everything that's one-size-fits-all is going to fit, because only certain percentages are in that center section. Let's take it a step further. In a group of 2,000 adult American males, about how many would you expect to be taller than 6 feet tall? Well, in this circumstance, we're talking about everything from here up. If I was to take all of the sections from there up, I would have this section right here is 13.5%. This section right here is 2.35. And based on the fact that it's 99.7% in the whole rest of the space, each of those side portions, 0, 1, 5, is 15 thousandths of a percent. Okay, so if you add all of that up together, you come up with 15.865%. And what this normal distribution allows me to do is say, oh, if I find 15, let's just round it off, make it 15.9% of the 2,000 American males we're talking about, I can figure out how many of those American males should be taller than 6 feet tall. And I end up getting 318. Okay, again, a useful thing to know if I am a developer of something where height matters for the person using it. Finally, a z-score. You transform a normal distribution to a standard normal distribution using z-scores. You can say that a value is 1 or 2 or 3 z-scores above the mean, or 1 or 2 or 3 z-scores below the mean. It's the number of standard deviations that x lies above or below the mean, and it's all about where does it fall in here. So if we know what the mean is above or below, and how far above or below. Use this formula. Z-score is equal to the data value in question minus the mean divided by the standard deviation. The data value in question minus the mean divided by the standard deviation. So if I want to find a z-score for each of these data points, if the mean of the set is 14 and the standard deviation is 2. So in other words, mu equals 14 and sigma equals 2. Well, I would plug it right into this value, this formula up here. My data value minus the mean divided by the standard deviation. In this case, -2/2, which equals -1. So that means that a data value of 12 is found right about here on the normal distribution. The second one, this one's above. So 17 minus 14 over 2. 3/2, which is 1.5, or 1.5, and that means that value is found halfway in between 1 and 2, right in here. And then you have number 3, a value of 10. So 10 minus 14 over 2 is -4/2 is -2. So that one is far below the mean. 2 standard deviations below the mean. If we're talking about test scores, that one would be quite low compared to everyone else. 2 standard deviations above would be quite high compared to everyone else. So this is a comparison value. That's the significance of these numbers. Finally, the number minus the mean over 2. So if I find the z-score of the number 14, I get 0 divided by 2, which is just 0. So the mean itself will have a z-score of 0 because it is neither above the mean nor below the mean. So that's a lot of information for one video. A lot of new information. I know you're probably feeling a little bit overwhelmed at some of this stuff, but try not to worry too much because once we get a chance to actually try it in class, I think you'll be much happier. I'll see you guys in class.